So far, we've defined the position, displacement, and average velocity vectors. So let's proceed on to instantaneous velocity. Okay, so we have these two positions at these two moments in time. But what if we consider two moments in time that were closer together? Say this moment and this moment. Let's draw on the position vectors at those two. Okay, position vector at that time and position vector at this time. And imagine the displacement vector between those two moments. So as the object moves from here to here over some short time, we can see that its displacement is going to point from there to there. So its displacement vector I can sketch in like that. That would be our delta V between those two moments. And we see that the displacement vector very nearly overlies the actual curved path itself. And we can imagine that the closer that these two moments in time get together, the very more nearly the displacement vector will be tangent to the path itself. The displacement vector will get smaller in magnitude as these points get closer together and become very nearly tangent to the path, such that two moments in time that are far apart have a displacement vector that doesn't bear much resemblance to the path between those 2 points in time. But as the time interval shrinks to 0, our displacement vector shrinks down to something infinitesimally small, but tangent to the path. So say at that particular moment right there, at this instant, we could define an instantaneous displacement vector. Let's call it dr, as in a delta r that has shrunk down to an infinitesimally small length. A little dr tangent to the path right there. So we've got an instantaneous, infinitesimally small displacement vector. Now, in analogy with our displacement vector here, our displacement vector of finite length, it having components delta x, delta y, and delta z. Well, as the time interval shrinks to 0, then the displacements shrink down to 0. So our displacements delta x, delta y, and delta z will shrink down to being infinitesimally small dx's, dy's, and dz's. And so our instantaneous infinitesimal displacement vector dr has components dx, dy, and dz. Remember that d means a very tiny, infinitesimally small delta. And it's going to be tangent to the path at all points. So I drew in a little dr at this particular moment. We can draw in drs at any other moment we choose. So over here, at this particular moment, we could have an infinitesimal displacement, dr, pointing tangent to the path in the direction the object happens to be moving at that moment. Let's say over here, at that moment, we could draw in a little dr tangent to the path. Okay, it's supposed to be infinitesimally small, but I have to draw it with, some length to it so you can see it. But the point is that it's tangent to the path pointing in the direction that you're moving. So we have little drs all along the path, like little steps forward. Each infinitesimal little step forward along the path moves the path forward. So all those little drs all added up, say all the drs added up between this moment and that moment, all the drs added up from here around to there, the sum of all those drs would make this big delta r right there. Let me suggest graphically how that works. If we have, let's see, starting from this moment and going to that moment, and we have this path connecting them. At each moment along the path, there's a little dr vector, dr tangent to the path, then another dr, and another one. All these little drs, these infinitesimal little displacements, each one tangent to the path at the moment. It looks like what I'm doing is making a chain of all these little displacement vectors. So if I add up all of these little displacement vectors, all these little drs, well, we know how to add vectors. And we know the head to tail method for adding vectors. So if I add up all of these drs, well, they're infinitesimally small and we'll need an infinite number of them to complete that whole path. So if I add up an infinite number of infinitesimally small displacements dr, what I'll get by the head to tail method is a sum vector that points from the very beginning of the chain to the very end of the chain, the delta r vector. So yes, indeed, the integral of all those little drs, the sum of an infinite number of infinitesimally small displacement vectors, would give us delta r, the finite displacement vector pointing from the very beginning of that path to the very end of that path. Okay, so that's our infinitesimal displacement vector. Let's now define our instantaneous velocity using that. Okay, so our instantaneous velocity is our instantaneous rate of change of position. So that's our infinitesimal displacement vector divided by some infinitesimal time that elapses. And our infinitesimal time that elapses, some small time interval, that is a scalar quantity. So our velocity at some instant equals dr dt, but 1 over dt, that's just a scalar. So what we've got here is the reciprocal of our little time interval times a vector. That's a scalar times a vector. So we see that our velocity vector at any given moment will be parallel to the displacement vector at that moment. And since our displacement vector is always tangent to the path, our velocity vector, our instantaneous velocity, is also always tangent to the path at any given moment. So going back to this picture again, we can note that at any moment, your velocity vector is tangent to the path. And it is not necessarily small. Your velocity vector could be some large finite value. So for each of these little drs, we can draw in a velocity vector that is parallel to it. Velocity always tangent to the path. After all, your velocity points in the direction that you're going, so it points forward along your path. So we can get the components of your velocity vector by taking the components of your instantaneous infinitesimal displacement vector, dx, dy, and dz, and sort of dividing them by the infinitesimal time interval dt. So our components of velocity vector are the derivative, dx dt, so the derivative of the x-coordinate of your position with respect to time, then the derivative of your y-coordinate with respect to time, and the derivative of your z-coordinate with respect to time. Since we know x, y, and z are themselves functions of time along your path, we take those time derivatives of these three functions to get Vx, Vy, and Vz, the x, y, and z components of your velocity vector. Okay, I think we can now make some analogies between the ideas we've developed and acceleration to conclude. So just like we defined change in position as a displacement vector, we can also define change in velocity, delta v. Velocity at time 2 minus velocity at time 1. So that'll be given by the x component of velocity at time 2 minus the x component of velocity at time 1, or the change in the x component of the velocity from time 1 to time 2. That will be the x component of the delta v. And likewise for the change in the y component of the velocity and the change in the z component of the velocity. Okay, so that's our delta v vector, the change in velocity from one moment to another. And you can see how, say, from this time to this time, the velocity vector does change. Here's the velocity vector at time 1. Here's the velocity vector at time 2. So we can take this vector v2 minus that vector v1 to get the delta v between those two moments. That's what we've defined right here. And we mainly need it in order to define average acceleration. Let's see, your average acceleration will come from this definition, delta v over delta t, except we're not in 1D now, we're in more than one dimension, so this delta v gets replaced by the delta v vector. So that delta v vector divided by the time interval that elapses, well, that's 1 over time interval, a scalar times a vector, so your average acceleration from time 1 to time 2 points in the same direction as your change in velocity from time 1 to time 2. So we get the components of your average acceleration vector by just taking the components of your change in velocity vector and dividing them by the change in time. So hence, delta Vx over delta t is the x component of average acceleration, delta Vy over delta t is the y component of average acceleration, and so on. And from that, I think it's a short logical jump to instantaneous acceleration. The acceleration vector at some particular instant in time t. Well, if your average acceleration is a delta v over delta t, then we get instantaneous values by replacing those deltas with the derivative, dv over dt, the infinitesimal change in velocity vector over some infinitesimal time interval. And so likewise over here, these delta vx's over delta t's get replaced with dvx's over dt's. So the derivative of the x component of the velocity with respect to time, the derivative of the y component with velocity with respect to time, and so on, give us the x component of acceleration, the y component of acceleration. Since the velocity components are themselves derivative of the position components, we can also express the x, y, and z components of acceleration as the second time derivative of the x, y, and z components of your position vector, d squared x, dt squared, and so on. And lastly, we note that just as your instantaneous displacement vector dr is always parallel to the velocity vector, based on this definition, those two vectors are parallel. Your instantaneous acceleration vector will always be parallel to the instantaneous change in the velocity vector. The little dv is always parallel to acceleration. Okay, and that's our full set of definitions that we need for vector kinematics.